All right. Hello, everyone. Welcome to another episode of Quirkcast. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. We're back after a week-long break, and so we're ready to jump into this. But before we do, if you're on the YouTube channel, please leave any comments or questions you have during the episode. We'll get to them. And if you haven't already, more guilt tripping, join our Discord channel so you can ask us more questions and we can answer with even more answers. So let's get to this. So I guess, Tim, I was thinking, like, I learned actually how to draw a circle recently, where they have this device thing that you can attach a pencil to, put it on and draw it in a circle. So my question then I thought of is, like, are there perfect circles in the universe? I just drew one. So what's the big deal?
Yeah, so good question. Yeah, I think to preface that, so we have to first define what exactly a circle is. So you can see all the drawings of circles. You might have some intuitive understanding, but I think we want to define circle as a more, I guess, like a abstract definition. A circle is a highly symmetric object. It's an object that kind of, when you spin around, it looks exactly the same. And I think when you give it that property, it's sort of like the unique object that has that property, that when you kind of rotate around, no matter how much angle you rotate around, it looks exactly the same. So that's why, in fact, that's why we have those devices that draw circles, right? You have a string attached, the string is the same length, so you kind of move around and hopefully you draw a circle. But I'm glad that you asked this question. There's sort of this general theme. I mean, of course, we're going to go back to the universe and life and all. There's this general theme is that, like, perfection is actually pretty damn tough. So if you try to draw a circle really hard, like if you're nitpicky, chances are you probably made some mistake. Like, it's not going to be so perfectly spherical. And in fact, probably if you draw on a chalkboard, on the computer, whatever, let's say on the computer, right? You can zoom into the pixel level and you'll see that it's not exactly symmetrical. So with that in mind, I would say at first glance, maybe not quite. It's hard to find a really, really perfect circle.
So I have a question regarding this. So what if, because I can see, because the pixels are arranged in a square-like format, you can get this like squares touching diagonally with the corner of other squares and like do it that way. But what if you were to redesign the computer so like all the pixels were like circles, like just these like layer of circles around each other? Then would that be a perfect circle or still not?
No, because the molecules are bumpy that make up the display.
Those cursed molecules.
I think you got to try harder. Try smaller.
Okay.
Right? Like, so
what if we go to like a particle, like an electron? I've always seen it drawn as a sphere, but like, is it a sphere? What's going on with that?
And the pictures they're circles, right? In the textbooks, pictures of particles are always represented as maximally perfect circles.
Yeah. What's wrong with that?
yeah, I think. Okay. So imagine you take like an electron. I think mathematically you can think of it as. I think it's pretty darn close to a perfect circle, but unfortunately, in the real life, the electron still would have some sort of, I think, like imagine you're trying to probe, imagine you're trying to look at an electron. Like, the mere fact that you're shooting something at the electron to interact with it, you're gonna mess up its shape, basically. So in some ways, in quantum physics, sort of like whenever you observe something, you have to interact with it. That kind of spoils the beauty of all the symmetrical things, it seems like.
Huh. So you're saying if I were to actually look at an electron, by look I mean shoot a photon at it or shoot some kind of particle at it to interact with it, that immediately perturbs the symmetry of it if it added to begin with.
Right, exactly. And in fact, I think I think this is sort of the interesting thing, right? The laws of physics has a lot of symmetries. And I think circles are sort of the building blocks of many of those symmetries. But so the symmetries are in the equations. But the funny thing is, when you look at real life scenarios, it seems like perfection, just like it's hard to find. It doesn't exist. Like if you really want to find that perfect symmetry, it's not there really. Like you dig really deep.
What? Why? Like what's so hard? I mean, I understand like it's an ideal form, but like what is the actual difficulty of doing this? Why can't we do it? Like
before we leave the discussion of circles that we draw, I just wanted to chime in and point out the fact, it's kind of an interesting fact, but like even with the example you gave with the, what's it called, a compass?
Yeah, just
draw.
draw.
Yeah. You only notice the imperfections if you look really closely, right? In fact, the farther away you get from the circle, the more it starts to look like a perfect circle. So there's a lot of examples like this in nature. If you look at the sun, for example, like from our distance, it looks like a perfect circle, or the moon looks like a perfect circle. But you don't have to get that close up to the moon to see all of the craters and all the bumps on its surface, but those kind of vanish when you're looking at it from far away. So yeah, it's kind of like when we talk about how it's kind of hard to find perfect circles in nature, there's a sort of pattern where a lot of these circles, they look perfect. And then when you look really closely, it's like, darn, there's like, you know, some imperfections or bumps on the surface. And that's kind of how it's progressed, I think, as far as the search for perfect circles go.
So
yeah.
One thing I want to ask, are you saying that if we stay an infinite distance away from anything, then there will always be perfect circles as long as you don't get closer?
Yeah, well, insofar as much as a point can be considered a circle, it is exactly has the same properties as a circle. But as you get farther away, yeah, everything would become a perfect point-like zero-dimensional circle.
There you go. We're done. Problem solved. What you can say, Tim?
Yeah, but not quite, because I mean, there's no infinities in nature, really.
Yeah, can you
like
be really far from something?
Yeah, I don't think that's fair. I think the next best thing is you can maybe ask the question, how perfect can we get to the kind of some of the most symmetrical things in the, I guess, in the world. Like
that is interesting though, like that, you know, exactly what you described, we're not done, because you can't get infinitely far from something. Imagine you start from close to it and you move far away. When do you get to infinity? Never, right?
Yeah, so I think there's sort of this theme here, like whenever you have some pattern or shape, if you zoom in, there's always these tiny little imperfections, and you can say, oh well, what if I try harder and harder? Well, unfortunately, quantum physics gives you perturbations, and no matter how hard you try, those imperfections are irreducible, right? So in some sense, quantum physics is sort of like the destroyer of symmetrical things. And particularly for artificial symmetrical things, like if you draw a circle, right? Like nature does not care to respect that circle. Like nature, like, you know what, Sahil, you draw a circle, but nature's like, I don't care for your circle. so quantum physics has no reason to respect your circle. So it's happy to throw some perturbations around it and mess it up. But actually, I would say there are some things that quantum physics respect slightly more. So
can you mention to our listeners what you mean by perturbations? Just quickly explain what that means.
Yeah, I think it's just like noise. I guess that's the best description, right? Perturbation, just like
fluctuations.
Yeah, just noise. Think of it just quantum noise.
Vibrations.
Yeah, I think that's fair. Just random vibration, anything.
But they had no small. Small is key. By definition, right?
Yeah.
So you have these fluctuations that just destroy any symmetry.
It has a strong tendency to destroy symmetries, especially man-made symmetries. It has a very strong tendency to destroy it. We don't care because we're not quantum mechanical. But if you zoom in quantum mechanically, it will almost by definition, almost always will destroy any symmetrical things, Sahil, you create.
I guess no perfect circles for me that I can create. But does it exist?
It's kind of poetic in that sense, though. It is like, you know, it sounds so corny to say, but like, you know, the order versus the chaos, like that balance is super real in the equations.
Yeah, so if it's real in the equations, like are we just not factoring that in when we talk about symmetry, or why is there symmetry even considered if it's not an actual thing? Like, at least superficially.
Yeah, it is a thing, but it's just not in the daily life's macroscopic things that we draw or visualize. I think to really find perfect symmetries, we have to go deeper, like to look at the fundamental symmetries of the world, something that the quantum physics will actually respect, you know, like not something Sahil you draw, but like laws of nature that even quantum physics cannot get around. They're like, well, too bad, you know, you can't violate those laws. We have some of those.
What would be examples of such things?
It's a little abstract. Let me think. Mikey, do you have some? We can talk about.
I think I ran into the same roadblock that you.
I guess, like, okay, let's suppose there are these symmetrical laws. Do they look circular in nature, like abstractly, or is there kind of a more super symmetric object, not to conflate it with supersymmetry in particle physics, but like, yeah.
It's a mechanism, right? It's a mechanism for forcing quantum mechanics to respect a symmetry. And a byproduct of that mechanism is what we see as forces of nature.
Yeah, so maybe I can, maybe to put it this way, like these are abstract circles. So so they're not like real circles, but more like abstract circles. So you can ask the question, like, what are they made of, these circles? Well, you can imagine you kind of have a periodic table. Let's say like periodic table of particles, right? A perfect circle in this way would be like relationship between particles. Like, imagine I have particle 1, particle 2, particle 3. Let's say they're related in some way. Let's say they're exactly the same, like their properties are exactly the same.
Okay.
Right? So you can maybe arrange them in a circle, 1, 2, 3, 4, 5, however many. And maybe that will create kind of like an imaginary circle made of the types of particles. And they will look exactly the same. If you spin the wheel and the equation changes, you spin the wheel again, it will look exactly the same, right? But of course, we're talking about an infinitely number of particles, you know, carefully labeled on a circle, and you can spin it around. And then the laws of physics remains the same, right? So that's the kind of perfect circle I think we're talking about. I think those in an abstract way exist.
So there's a question I have. This might be getting way into abstract territory, so feel free to let me know if this is like too off the rails. But is it a circle that you necessarily can't really, like, quote unquote measure? But if you don't measure it, it's there. But if you like measure it, there's a particular instance in which you see of the circle, much like how, slightly technically, you have phase factors and you don't actually observe an actual phase factor by itself. So it's like a circular type of thing. And so that vanishes away. So it's like this circle if you don't actually do anything to the system and just is there. But if you like perturb it, or things like symmetry breaking, that's just all gone in a certain sense. So I'm curious, like, is it just that the symmetries exist, but they're broken through whatever you want to call this, all this stuff around us that happened, or like, do they still actually exist in a certain sense?
I want to push back against the idea that these circles are abstract and we shouldn't think of them as physical, because a lot of these ideas that we're talking about, like the interpretation, let's take the electromagnetic force, for example. The electromagnetic force is determined by the symmetry of circle that we all know, the circle that you can draw on a piece of paper. theories of electromagnetism can be derived by imagining that space is actually curled up in the shape of a perfect circle at a very, very, very small distance. And if you imagine this universe where space is curled up as a very, very, very perfect circle, if you look at it microscopically, you zoom out and you get this phenomenon that we call electromagnetism. So that's at least one way to interpret how forces arise from these circles, if that makes sense.
What do you mean, like a really small, like when you say a circle is like wound, it looks like it's winding upon itself, but it can't really wind upon itself, right? Like, do you mean like, I don't
It
know,
actually could.
or-
That's
By what they call a winding number.
oh yeah, that if you wind around those circles, that's a monopole, right? But let's not get ahead of ourselves.
Yeah. Well, I'm just wondering, how can you have a circle and like have it wind on itself? Like, is it not just a 1D circle, right?
A lot of these theories are easier to imagine. Like we think of the universe as like a box, right? But you could very well imagine it. Like if you go in one direction for so long, imagine you come back to the place you started, right? Like maybe it already wraps around, but at a very large distance. And then you imagine that just shrinks.
Yeah, well, yeah, I think the mathematics, I think this is exact, right? The mathematics of electromagnetism has to do with geometry. You literally visualize. I guess, Mikey, you're right. So the fact that the electron has a charge and it can interact electromagnetically, if you think about it geometrically in this picture, it's basically like the electron is actually moving in those circles, like in the imaginary table. It's all actually changing types of electrons. Imagine you have like a clock of which type of electron it is. Like the fact that electrons move around in an atom is just the interaction can be described by the electron moving around in some particular circular way, right? So I guess in that sense, yeah, if you interpret it that way, that can be very real.
I guess then the natural question that I would ask is like suppose they take your word for it, these symmetries are here. What happens when we like go to a classical level? Like me myself, I look at something, I don't see those symmetries. Like why are they washed out or look washed out? Or they're not like there? Like why can't I?
For electromagnetism, that symmetry we do see. I mean, the existence of that circle, the fact that the electromagnetic force is a long-range force, it survives to macroscopic distances, is exactly that circle. You know, the existence of that circle communicating itself to our experience, I think.
What do you mean that circle is existing and is it like the 1/r² law? Is it like in what form does it appear? How do I know that these things are circular?
I think that's it. I think Mikey is right. The fact that this symmetry exists, that's the realization of it, that we have electromagnetic forces. Maybe a more intuitive way of thinking about it is this. Like imagine really there are these infinite number of electrons arranged in a circle. Mm-hmm. Each one is absolutely identical to another. Imagine this is really real, right? And let's say you have like one electron. You wouldn't really be able to tell where in the clock this electron belongs to because they really are exact. so it's almost like, because it's so perfect that you wouldn't think that it's different. Like imagine, Sahil, if you had a perfect twin, think exactly in the same way, do exactly the same thing. Well, actually, it will probably occupy exactly the same space, even though it's not possible. Like that's what perfect symmetry is. It's just so perfect that, that will just be one Sahil, basically. I think that's where we're at. Like this perfect, if this perfect symmetry is perfect, you actually wouldn't think of them as distinguished things. You actually think of them as the same thing. So I think that's the realization of it, that the electrons have their symmetries, and the manifestation of it is that, well, we can't see the circles just because they all look the same. But the manifestation is that there's a force that kind of comes up to it, although it's sort of in an indirect way. I think this gets pretty technical, right?
If we go on this analogy where you have this circle with like infinite different, like same electron, but just maybe different positions of the circle, and you do some kind of observation or you see this electron in an experiment, you're only picking one out of these like infinitely many, right? So wouldn't that be breaking symmetry that way by picking one of those infinitely many electrons, even if you can't tell the difference between all of them in some sense? I'm going based off this analogy. I don't know how far this analogy carries. Just want to.
I'm tempted to say that the answer is yes, and that the manifestation of that symmetry breaking is the fact that the trajectory is no longer following what it would.
Well, it's a little technical. I think there's a different perspective that you might actually think that maybe if things are really identical, maybe the circle doesn't really exist, right? Like if that, this is another perspective, right? Imagine it's almost like, hey, imagine there's a perfect copy of Sahil, even though it's not possible. Like that sits exactly in the same place as Sahil, does exactly the same thing. Everything is symmetrical, while maybe there's only really just is one Sahil. So we can only tell if there's more than one Sahil when there's some difference that's manifested, basically. Yeah. Right. We have to eat
100 clones, but the clones were so good that they did exactly what you did, and that's exactly the same place as what you did. Then would they really be clones?
That's my struggle when I look in a mirror. I'm just like, who's the real?
Yeah.
Is it me or the other guy?
Like, yeah, I think that's, well, in a weird way, I think all the forces that we know, that's how, like, we call these like gauge forces. That's how they operate. They kind of presume that first there has to be some symmetry that tells you, hey, things are really identical. But then forces arise when these differences are accentuated, and these differences causes interactions.
Oh. So what if we go to the case of like gravity, like a single, I mean, there's no such thing as a point particle, but if I look at like a point particle in classical physics, it says the gravity around is like only dependent how far you are away. So there's this kind of rotational symmetry about it. Is it like, does that apply, or is that not applicable, or I don't know?
Yeah, because it's actually like gravitons communicating the force, right? The density of gravitons is not going to be exactly the same everywhere. So yeah, that's actually patently false.
Okay.
Wait, no, I think this is a little more unclear, right? In some ways, in some ways, if you think of the directions of like up, down, left, right, you know, if you think of them as the more realism, you know, if you think of it as the what we see in reality, like actual space-time, yeah, you know, things are different because there's Earth, there's galaxies, dark matter, yada yada. So up, down, left, right, front, back, it's not really exactly the same. But if you zoom in microscopically, you can also think of up, down, left, right, front, back as sort of like, if you think of space-time as what we call dynamic, like if the fabric of space-time can also fluctuate, then they become abstract directions, just like, you know, different positions of, you know, the different locations of electrons in a circle. You can think of these different directions as kind of different abstract directions the graviton can move to. But gravity is really weird. But when you think of it like this, you can think of the gravitational force as arising from that, the difference of that. So I don't know. This is probably only confuses people, but gravity is very strange. So maybe that's not the best place to draw inspirations from yet.
I guess we can come back to the original question, like, do perfect circles actually exist, or are they more inferred? Is it just that the theories that we use to describe these things have perfect circularity, but we don't know for a fact in the universe that there actually is perfect circularity?
Yeah, I mean, if there can't even exist perfect circularity in the laws of physics, then I think a reductionist would argue that it could never arise in any macroscopic way. Then. So yeah, I would say that the existence of a perfect circle necessitates at least the permittance of perfect circles in nature. Right? If you can't have one, then the other is kind of screwed.
Yeah.
Well, we just talked about how we can't find perfect circles in nature. Like they don't exist macroscopically. Like, they're not there.
Yeah, I think.
If any of these symmetries are real, you could imagine constructing, at least theoretically, a perfect circle. Is that true?
Well, I mean, you can argue, like, how do you even define a perfect circle? Like in the universe, what does it even?
If it's out the boundary of a perfect circle in any way, I would say you've won. So if you could even like create a system where the, I don't know, in string theory, where like the string, yeah, if connected strings can even form perfect circles.
I feel like if you were to define what a perfect circle is, the kind of circle we just described, I think that's the only sensible definition. It's really a fundamental symmetry that's just written in the laws of physics. And to measure it, you just probe the laws of physics. Is there a more sensible definition? Because
so it's just that the theory has a geometrical equivalence to being represented by a circle. Is that more of what you want to say about it?
Yeah, I feel like because you can never really totally measure a system. So how can you ever fully measure a full circle? Like, I feel like that's
literally if you take a universe and you just wrap one of the dimensions around in a circle and shrink it, you literally get electromagnetism. So yeah, I don't know. I don't view it as this inferred abstract thing that is kind of like a model, because it can arise in a real physical, tangible way.
What? Sorry, I'm so confused. What is the real physical, tangible way? We just talked about making the universe enclose upon itself. Like, what is the real physical tangibleness of that? I'm curious.
Like, so if this is true, if electromagnetism is a perfect circle, then you could potentially inject enough energy to blow up that circle and observe its perfection in some way.
And you can wreck it. I guess with the moment you can blow it up, you can kind of wreck it a little bit. You can perturb it.
Yeah, but it must be at least possible if it's a perfect circle, at a small scale.
Well, we already perturb it. The perturbation is electromagnetic radiation, if you think of it that way. So it's like, wow, it's like it's perfect, but it needs to be able to, like, you have to be able to perturb it.
Yeah.
So the act of seeing it is kind of like you destroy it. But I think we give ourselves a pass on that. Like this is okay.
My question for you then is like, if you don't observe any of these things, but there's still quantum fluctuations or this noise happening, can it actually exist? Because it's like, it's unremovable. You can't get rid of it. And it's like there at all levels, right? Or is there a level where it does not exist? Physical theories, like, I don't know, do they capture this fluctuation within the structure of the circularity?
Wait, sorry. So quantum mechanics respect that circularity, whatever that is. It respects those symmetry. Yeah, like that's what's different,
Even with the fluctuations going
on. Yeah, the fluctuation, you can think of them as fluctuations of electromagnetic radiation. But again, I think we give ourselves a pass on that. It's okay.
Yeah, I don't know if I'm being too loose here, but in a sense, like the fluctuations are in the direction of the symmetry for those special cases.
Yeah. Yeah, the fluctuation does not break the symmetry in some ways. It's just kind of like a pulsing, I guess, of the circle. So it's more like, it's okay. It's still a perfect circle, I would say. Close enough.
I mean, none of these are practical circles. So, when we ask the question, can perfect circles exist in nature? We find like better and better examples that are harder and harder to access, like the electron. We couldn't access that till 100 years ago. So then we get into the game of like, what if I had like infinite resources? Could I imagine making such a thing? Yeah, I think that's really the question of what we're talking about here.
Yeah, so could you, with infinite resources and time, make a perfect circle?
If they exist, then I think you can. I personally don't think that they exist. I mean, I'm a minority camp here that thinks that if you look at any of them close enough, you'll see things breaking, but
Couldn't you say it's just a perfect circle, but with noise on it? Like without the noise, it would have been a perfect circle. Just because of the noise, we can't ever see a perfect circle.
I mean, then to what extent is that noise? It's a triangle, just circle plus a lot of noise. Then
particular noises.
like
Oh,
we could play that game, yeah.
Well, let me ask you this. What would happen if there wasn't perfect circularity? Like at least if that just could not exist, or these theories were not perfectly circular, like what would that mean?
Well, the mathematics will go to hell, actually. Like maybe real world it'll be okay, like because we don't really know what real world looks like, but some of the mathematical foundations of these like physical laws, they have to respect those symmetries. Like I say, that's the reason why even quantum physics, we believe, will have to respect some of those symmetries, like the fact that certain things are circles, right? Otherwise, if that's not true, then our laws will have to be rewritten. Like the mathematical framework would not work anymore. It will be kind of messed. Like the math would just be wrong. Then we have to rethink. But I don't think we know how to deal with that yet.
And then what about more of discrete symmetries like boxes, triangles, pentagons, all that stuff? Like the circles, like why only circles? Like does a perfect pentagon exist? Does a perfect square exist? Like what are these discrete symmetries?
Wait, before I talk about discrete symmetries, I just wanted to add to that. I think, you know, if it's, there's at least one scenario interpreting the question you asked. If you assume that ultimately the laws of physics are not ordered by any symmetry, then it would mean that the laws of physics we have, though maybe valid, would be like, you know, pure coincidence almost. Like it just happened to look symmetric this way because someone threw darts on a board, and you know, 1 in a billion will be this way, and that's where we are. Yeah.
Wait, and before I think we answer the question of these smaller symmetries, I think we should go bigger first. Like it's a perfectly valid question to be like, well, who cares about the circle? Why are we talking about circles? Like I think the way we're framing it, like when we say circle, we really just mean symmetries. And circles conveniently is sort of like the smallest interesting symmetry. That's, you know, because there's infinitely many rotation and whatnot. And all the bigger symmetries are just built up of different circles nesting together. You can think of it that way, right? You can have multiple circles left and right. The electromagnetism is like a circle. The strong force, you can think of them as many different circles, different colors and whatnot, and so on and so forth, right? So that's looking at, you know, to more symmetry. And to your point, Sahil, they're also like a smaller symmetry, like a box, right? Like a square. Like you can, so once again, there's this question of sacred versus not sacred symmetry, right? If the box is something you draw, Sahil, quantum mechanics is not going to care. Like, sorry, it's not going to care that you draw this box here. But if the box that you drew, let's say it's the remnant of a circle, let's say the circle got deformed slightly by some force of nature or whatever, it turned into a square, then that residual symmetry may have to be respected by quantum physics. And that might actually, you know, we might actually see it. And an example would be like, imagine the corners of a box. Maybe we have 4 different particles that look they have exactly identical physical properties. Then that would be a hint of like, you know, such a symmetry. So,
Wow. So there's also an audience question that I want to ask before we, you know, we're running up against time, so I want to get a chance to ask this. So an audience member, Tim, for you, is asking, how can I better appreciate what Tim said regarding infinities that don't really exist in nature? We were talking about zooming out to infinity, see everything as a point, and then perfect circularity exists.
I guess the question is sort of directed to me.
Yeah.
Yeah,
or,
I think
or
it's just
anybody who heard you. It's also equally valid.
Yeah, well, I think it's just a theme of nature that infinities don't exist. because science is practical. You cannot measure infinity. I guess you can measure 1 over infinity, which is 0. So, but infinity just doesn't exist. You can never fly infinitely away. Sure, the universe might be infinite, what we think, but you can never measure that sort of infinity, right? So I think generally when people try to ask, so sometimes it happens that you might get infinity as an answer, but that's usually when you ask the wrong question to physics, right? Physics is sort of like, physics is smarter than you are. So whenever you ask sensible questions, you should not get infinity.
Oh, all right. Hear me out before we head out. The universe is infinitely large. Couldn't you say it's a perfect circle? Because an infinite box is the same thing as an infinite circle. Is that a fair point? Or
well,
Essentially,
I don't know.
a good argument for why the universe probably isn't infinite.
Yeah, there's another point. Yeah, maybe it's not infinite. I don't know. Infinite, not well. You cannot verify it, right?
No, you can't verify this. It's just a speculative thing. Well,
Yeah.
so I guess, Tim, do you maintain the position that you're not necessarily in some abstract notion, but in some notion, perfect circles do exist? And then Mikey, you're just like, no, even if you look close enough, they're just not there. They just appear to be there, but they're not actually there. Is that a fair assessment?
I changed my mind. I actually think they are there.
Did I convince you, Mikey?
I thought I convinced you, so I'll take the credit for that one, Tim. All right. So before we head out, do you want to leave our audience with any last thoughts?
Yeah, I don't know. I think if I had to be speculative, I would say that, yeah, the existence of like the fact that circles exist, period, in our everyday life, the fact that the moon or sun look approximately circular, all of that stuff are kind of reverberations of, symmetry that has like a higher fidelity at a smaller scale, because, everything is built from other things. And yeah, it's kind of interesting how these patterns repeat themselves, and oftentimes they're a clue of what could be deeper. So, yeah.
Yeah, I guess I can sort of add to that. Do we sort of come into some sort of agreement? Maybe not. Maybe a slightly different perspective. I guess, yeah, this is an interesting question. I think for all intended purposes, like if so it's hard to answer this question, the perfect circle exists, because it's hard to define what a perfect circle is. But I think we try to define it. The closest thing we can get to is these fundamental symmetries of the universe. Like those are the closest perfect circles. I think in that way, yes, they exist.
So all you do is just go to level of quantum mechanics and circles with respect to its symmetry, and then I'll be circular.
Yep.
All right then. Well, I have my next drawing task. I'm going to use the force mediators to draw one, and then we'll take it from there. So I'd like to thank everybody for joining us on this exciting episode, and we'll see you all next week.
See you all next week.
Yeah.
Bye.
Bye.